Okay, let's resume with our next speaker, Andy Neitzke from Yale University. He's going to give his first of his two talks on BPS states and Riemann-Hilbert problems.
Great. So thank you very much for the introduction and for the invitation to speak here. It looks like a great conference. I've already learned a lot. I'm looking forward to the rest of the week. So my talk is on BPS states and Riemann-Hilbert problems. And this is an account of a particular kind of geometric application of the theory of BPS states. And it's an application which I first came to understand in joint work, which is now like more than 10 years old, with Davide Gaiotto and Greg Moore. That work was based on ideas of a lot of people, whom I've listed some, but by no means all of them here. And more recently, I've been working on closely related things in collaboration with various people, including David Dumas, Laura Fredrickson, Dan Fried, Alba Grassi, Chen Yu Hao, Sebastian Schultz, Ali Shepper, and Fei Yan. And there's been a lot of work in kind of related areas, and I listed a few of the people who are working on things kind of close to this Riemann-Hilbert problem. Okay. So what's the story? I'm going to tell you in this talk. I'm going to tell you basically an old story. So the story is like this: if someone gives you a four-dimensional n = 2 supersymmetric quantum field theory, and we won't need to know in detail what that is, but the physics story is someone gives you a four-dimensional n = 2 supersymmetric field theory, then there are physics arguments that predict that there ought to be a corresponding hyperkähler manifold that you can build. And physics also predicts a kind of recipe for how to construct that hyperkähler manifold. And that recipe turns out to involve solving a kind of interesting Riemann-Hilbert problem. You're looking, very roughly speaking, you're looking for functions on CP1 with some very particular analytic structure. And so that's the story I'm going to tell. One of the reasons for giving this talk now is that this Riemann-Hilbert problem is almost the same as one which is kind of recently in the news, because it's shown up on the one hand in work of Tom Bridgeland on kind of also on geometric uses of Donaldson-Thomas invariants, but different ones. And it's also kind of close to things that are showing up in work of Coleman, Longy, Plumoni, and Teschner on kind of, I would say, non-perturbative topological string partition functions. And so I'll try to discuss those connections next time, not today. So the starting point for what I say today is, as I said, it's an n = 2 supersymmetric quantum field theory in 4 dimensions. I won't try to say precisely what that is, but I'm just going to axiomatize some of the kind of geometric parts of the theory. So some things that you're supposed to get if you have an n = 2 supersymmetric quantum field theory, and I'll explain what they're believed to be in some kinds of examples. So in particular, if someone gives you an n = 2 theory, one thing that they're supposed to be associated with it is they're supposed to be associated a complex manifold. I'll call it B, and it goes by the name of the Coulomb branch. If you want to know what it is kind of in physicist language, what it is it's a space of possible vacuum configurations of the theory when the theory is formulated in the space-time R4. So you put the theory in R4 and you ask, what are all the possible kind of lowest energy configurations it can settle into? It turns out that those configurations form a kind of nice structure. They form a complex manifold. In fact, it's even Kähler away from some kind of bad locus. And I've marked that bad locus. It's codimension 1. That's a locus where the low energy physics is actually more interesting. And so I've marked it with the orange dots in this picture. In the picture, I draw B as if it was one-dimensional. In general, it could be higher dimensional, but actually there's already interesting examples which are one-dimensional. So for thinking about this story, it's perfectly okay to just think about the case where the Coulomb branch is one-dimensional. And then there are, okay, so there's a complex manifold, even a Kähler manifold, but it comes also with some extra structure that the theory is supposed to produce for you. So one thing it's supposed to produce for you is at every point U, it's supposed to produce a lattice, a finite rank lattice, gamma. So really I should write gamma sub U, and you should think that this is like a local system of lattices, where as we move around the Coulomb branch, there can be monodromy. But writing that U every time gets tedious, so I just write gamma for the lattice. And it comes with a pairing, a skew pairing, a skew integer valued pairing. And the way you can think of this lattice is that it's keeping track of all the charges of particles in this quantum field theory. It's keeping track of their electromagnetic charge and also some other thing called a flavor charge. It's fine to think of the case where there are no flavor charges, only the electromagnetic charge. And then there's another piece of data which, so that first datum, the lattice, you could understand perfectly well just think about ordinary electromagnetism. The second datum is a little more exotic. It really has to do with supersymmetric theories, and that's a homomorphism from the charge lattice to the complex numbers. And that's called the central charge homomorphism. And then as you move around on the Coulomb branch, that homomorphism is supposed to vary holomorphically with U. So if you like locally, what it gives you is a bunch of holomorphic functions, and they have some monodromy when you go around the branch points. So in examples, they might be like hypergeometric functions, something like that. Okay. I see. Okay, I'm accidentally showing you the version of this slides where I don't have the pauses in. Maybe I'll try to get the version with the pauses. Sorry. I apologize. Just because it'll be nicer. Okay, wonderful. So I just told you that if someone gives you an n equals 2 theory, there's some data associated with it with its low energy physics, which is a complex manifold with a local system of lattices over it, away from a discriminant locus. And then for each of those lattices, you have a homomorphism to the complex numbers, which varies homomorphically. Okay. Now, there's another way of organizing that data, which is a little bit more, geometric sounding right off the bat, which is that what that data gives you is it gives you a complex integrable system over the base B. So B again is our Coulomb branch. I'm saying it has lying over it this complex integrable system, which is a holomorphic symplectic manifold with a projection M to B, a holomorphic projection, such that the fibers are complex Lagrangian with respect to this holomorphic symplectic form. And here's a picture of what it might look like. Okay, strictly speaking, it depends on a little bit of extra data. In the case where this pairing is not where this pairing is not non-degenerate, then you need to have some data having to do with the kernel of that pairing. But it's not so important. But the picture that you want to have in mind is that the generic fibers of this complex integrable system are tori, literally a compact torus, which you think of as being like the torus of characters of the lattice gamma, all the maps from gamma into U1. I'm overlooking some twisting by signs, which is kind of painful, and I'll systematically ignore some signs throughout this whole talk. So we have this complex integrable system. Well, I told you where it comes from in the C infinity world. I told you what the fibers are. I didn't tell you where you get the complex structure in the holomorphic symplectic form. Where that comes from is these functions Z. So there's a sort of cryptic looking formula which describes the holomorphic symplectic form. It's determined just by the derivatives of Z. Okay. So having these this local system of lattices together with these functions from the lattices to the complex numbers determines for you this complex integrable system over the base. Okay. Now, okay. So far, I told you what I would say is kind of the boring part of the data, and now I want to tell you the most interesting part, which is that for every point of this base, the Coulomb branch, the base of this complex integrable system, the quantum field theory is supposed to produce for you one more thing. And the thing that it produces for you is a vector space, a graded vector space, which you think of as being for each possible charge, it's telling you the particles with that charge. Strictly speaking, the so-called BPS particles, supersymmetric particles. Roughly, it's the vector space of states of particles with that charge. It's a representation of SU2 because it's double cover of SO3. You have a particle sitting in 3 dimensions. Its states naturally form a representation of SO3 or its double cover. So there are these vector spaces, which are the spaces of BPS states, one particle BPS states. When we formulate the theory in just where the space is just flat space R3. You look at all the states that a particle can have. From this vector space, you can construct some integers. Okay, this integer is just counting the representations in some slightly tricky way. But it's an integer that you assign to every representation of SU2. And so those are some numbers with a sign. They can be positive or negative, which are keeping some kind of graded count of these BPS particles. And for the rest of the talk, unfortunately, I'm only going to use the integers and not the whole vector spaces. So there's a bunch of numbers which the theory produces for you. So far I just told you some kind of axiomatics. I told you a bunch of data. I told you there's something called n equals 2 theory, and if you have that n equals 2 theory, you got a bunch of data. I kind of listed out the data. Now I want to make this more concrete, so I want to tell you what all these data are and some specific class of examples. And the class of examples I'll tell you about is the so-called theories of class S of type A1. And in that case, all the data are related to the geometry of Riemann surfaces. Okay, so now I kind of start again. So suppose someone gives me a compact Riemann surface, and it might not have any marked points, but it might have some marked points. And then at each marked point, I'm going to fix some singularity data, which is going to be some information about singularities of a quadratic differential at that puncture. So for example, one thing you could require is that it just has a first order pole at the puncture, then there's no other data. Another thing you could require is that it has a second order pole, and then you would fix the residue. There's analogous things for higher order. Okay, so suppose we give ourselves that kind of data, just a Riemann surface with punctures and some data at the punctures. So that data is enough to determine an n equals 2 theory. It's called S of A1 and C. And in that theory, now let me start telling you what all the data is. So the first thing, the most basic thing is what's the Coulomb branch? The Coulomb branch is going to be the moduli space parametrizing meromorphic quadratic differentials on the surface, where the singularity at each puncture is constrained by the data that I fixed. Okay, so this is a story about Riemann surfaces equipped with meromorphic quadratic differentials. Okay, and so given the Riemann surface and the meromorphic quadratic differential, the first thing we do is we build this other curve called the spectral curve. And the spectral curve is just, it's nothing fancy, it's just a two-sheeted covering of C, whose two sheets are the two square roots of the quadratic differential. So it lives naturally inside the cotangent bundle. It's a double cover of the curve. Actually, it's a branched double cover. It's branched when the two square roots come together, which is to say exactly at the zeros of the quadratic differential. Okay. Okay, so in fact, instead of saying I study surfaces with quadratic differentials, I could just equivalently say I'm studying a surface and a double cover of it that lives in the cotangent bundle. Okay. Okay, so I told you what's the Coulomb branch. Now we were supposed to have this local system of lattices. So what are the lattices going to be? The lattice. So once I pick a point in the Coulomb branch, I have a particular double cover here, and then the lattice is just going to be the homology, the first homology of this double cover, first homology of the spectral curve. Except more exactly, we take the odd part. So this double curve has a Z2 involution, just exchanging the sheets, and we only look at the cycles that are odd under that involution. In all the examples of cycles that we'll draw, we'll automatically have that property. Okay, so roughly speaking, it's just the first homology of the curve. So we're studying a family of curves and their first homology, their H1. And then I'm supposed to give you a number for each, when I have the data of the curve sigma and a cycle on it, I'm supposed to give you a number, the central charge, and that number is just going to be the period of the tautological holomorphic one form. So because this curve sits inside the cotangent bundle, there's this tautological one form, the Liouville one form, and we just take the periods of that. Okay. All right. So, okay. So now the most interesting part is these integers, omega of gamma, which I said are counting BPS particles. And so what are they in this case? The things that you have to count, which are like kind of the classical avatars, if you like, of these BPS particles, the things that you have to count, it turns out, is just geodesics on the curve. Well, geodesics in what metric? If we have a holomorphic, meromorphic quadratic differential, then we get...
sorry to interrupt. There's a question in the chat.
Oh, yeah. Great. Just speak out. Let's see. What is H gamma here? Where did I write H gamma? Is that a typo?
I think it was at the previous slide, or at least that's where the question was asked.
I think they're
BPS
referring to maybe
subspaces,
Z gamma.
Z gamma,
Oh.
yeah, that's here.
No, I think the question is about
no.
the BPS subspaces.
Yeah.
Oh, what is the actual space? No, that's a good question. So I don't know how to make that space. Yeah. So, well, I guess there is a way of making it. There's a way of making it in terms of like quiver representations. But basically, I'd like to say I don't have a really good answer to this question. And in general, the story I'm going to tell, kind of parts of it have been categorified and parts of it haven't. So I don't have a sharp mathematical answer to this as I would like to. Okay, so but let me say what the decategorified thing is, what the numbers are. So we're given this surface with a meromorphic quadratic differential, and in that situation, we get a metric on the surface. In fact, a flat metric, which in local coordinates is just you take the square root of the absolute value of the quadratic differential. That naturally gives you a metric on the surface, which is flat. Now, of course, you can't have a flat metric globally on the surface. This metric has singularities exactly at the zeros of the quadratic differential and at the poles of the quadratic differential. And what we're interested in is counting the finite length geodesics on the surface with respect to that metric. So there's two ways that you can get one. Well, there's two main ways that you can get one. One is to have two zeros of the quadratic differential and just have a straight line trajectory that connects one to the other. That's what I've drawn on the left here. And the other is you could have just a closed geodesic, a closed loop. And that's what I've drawn on the right. And in that case, it actually comes in a one parameter family, an annulus, and I've just drawn one of them. So those are the two kinds of BPS particle that you can have, and then they contribute. So this guy on the left, this geodesic segment contributes omega of gamma equals 1. Well, you can ask, which gamma does it contribute to? Well, in the picture, I've drawn a cycle gamma on the double cover. I just lift that segment up to the double cover. There's a loop there, and that's the charge of this BPS particle. So it contributes omega of gamma equals 1 to that particular gamma. And then on the other side, when we have the annulus of closed trajectories, that contributes, oddly enough, omega of gamma equals -2. It corresponds to a particle which is a vector multiplet instead of a hypermultiplet. Omega gamma equals -2 for the gamma that I drew on the right there. So that's the definition of these numbers in this particular case. And okay, so now I've told you all of our data. I think. All right, so let's talk about, let's make it really concrete. Let's talk about the simplest non-trivial example. let's take the surface to be just CP1, put a single puncture at infinity. And in that case, in order to get anything non-trivial, I have to allow singularities of rather high order. So I'll write the meromorphic quadratic differentials in this form. It's a cubic polynomial plus lambda z for some fixed lambda plus u times dz squared. And the way you should think of it is that lambda is something that's just fixed for all time. It plays a role kind of like a complex structure modulus of the curve, and u is the parameter that we allow to vary. So then the double covers that we're talking about are literally just these cubic curves in y and z parameter, just obeying this equation. So that's a genus 1 curve, right? Sitting inside of the cotangent bundle. Well, it's CP1, but it has a singularity infinity. So you might as well think it's cotangent of C. In other words, just C2. So literally, we're just talking about like cubic curves in C2. And so in that case, the homology, the first homology of such a curve is just a lattice of rank 2. And here are two, here's a kind of concrete picture of what it might look like. So here I'm presenting it as a covering of the Z-plane. It's a double covering of the Z-plane, branched at 3 points, the 3 zeros of that quadratic differential. And so you can literally draw 2 loops that generate this lattice. And then the central charge, to get the central charge function, you integrate, well, the tautological 1 form in this case boils down to just literally the square root of the quadratic differential. It's y dz, and y squared is the quadratic differential. So you wind up doing these kind of very concrete integrals in the plane. Okay. And then you could ask, what are these BPS counts in this example? And here it turns out to depend on what the parameter u is. It depends on how the zeros of this quadratic differential are lined up. And depending on what the parameter is, there can be either 2 or 3. So for example, on the left, I drew a situation where there's just 2 of these finite length geodesics, one in class gamma 1 and one in class gamma 2. And so then this omega is a function on the whole lattice, but it's 0 almost everywhere. It's supported just on these 2 charges, gamma 1 and gamma 2, and then also minus the charges. As I've drawn it, I didn't really specify natural orientation, and the reason is that the invariant is the same for plus gamma and minus gamma. So in the situation on the left, this omega is just supported on 4 lattice vectors, and it's equal to 1 on all of those. And in the situation on the right, there we've sort of moved in the moduli space, and now we have 3 of these things instead of 2. We have 3 finite length geodesics, and correspondingly, this invariant omega is now supported on 6 lattice vectors instead of 4. And so there's going to be some place in the Coulomb branch where the invariant suddenly jumps from 2 to 3. So as I continuously move from the picture on the left to the picture on the right, there has to be a moment where one of these geodesics appears. And so that's the so-called wall crossing phenomenon for this BPS index. It's not locally constant. It's only locally piecewise constant. Okay. Okay, so that's a prototype of the kind of data that we might be talking about. Just some concrete family of curves, concrete period integrals, and these integers. So one comment about these BPS indices, there is a kind of general expectation that in any n equals 2 theory, the BPS, it should be possible to think of these BPS counts as some kind of Donaldson-Thomas, generalized Donaldson-Thomas invariance. And in complete generality, that's only a dream, but in this particular case, it's actually been proved in work of, well, in the punctured case, in work of Bridgeland Smith, and then very recently there's work of Fabian Hayden in the unpunctured case. So the statement is that given all of our data, particularly given this curve with the specified punctures and specified singularity data, there is some category, some 3-Calabi-Yau category, such that the data of a meromorphic quadratic differential determines a Bridgeland stability condition on that category. Okay, if you don't know what these things are, as I in fact don't know exactly what they are, but I know the correct statements. Don't worry, it won't be used in the rest of the talk, but I thought it's a nice connection to this generalized DT theory. So in this case, the integers omega of gamma are in fact the generalized Donaldson-Thomas invariants counting semi-stable objects in this category relative to your given stability condition. And then in some cases, when C has kind of sufficiently strong punctures, particularly it has to have at least one pole of order, at least two, then you can also identify these omega of gamma. This is part of the work of Bridgeland and Smith. You can identify them with generalized Donaldson-Thomas invariants associated with quivers. I mentioned that because, if I understand right, Pierre Clouseau is going to give a talk where he introduces the theory of DT invariance of quivers. So I want to say these objects, in some cases, can be identified with those. Okay, and one more thing to say about this is that the category. So I said that there's, given your Riemann surface, there's some 3 Calabi-Yau category out there, and one geometric interpretation of that 3 Calabi-Yau category is it's actually the Fukaya category of a certain Calabi-Yau threefold, certain non-compact Calabi-Yau threefold. Which, right, I guess more exactly, to get the Calabi-Yau threefold, you need to fix a stability condition. So you choose a particular stability condition that corresponds to a complex structure on this Calabi-Yau threefold. And then having done that, the threefold is given by this equation: x squared plus y squared plus w squared equals phi 2 of z. So one equation in 4 variables gives you a threefold. And so from the physics point of view, the reason why you kind of expect this is that the quantum field theory you're studying is actually dual to string theory, type 2B string theory formulated on this Calabi-Yau threefold. And then there's a nice picture that goes along with it. So the generalized DT invariants of the Fukaya category, what they're sort of expected to count is they're expected to count, it's some version of counting special Lagrangian 3 cycles inside of the Calabi-Yau. So what does that have to do with these geodesic trajectories? Well, the story is supposed to be that when you have a geodesic trajectory in your curve, which begins and ends on zeros of the quadratic differential, you can lift each point of that trajectory. You can lift to an S2 in the fiber, and that S2 in the fiber collapses as you go to one end or the other end, as you go to the branch points. So they kind of sweep out an S3. And that S3 is a special 3 cycle in the Calabi-Yau. Okay. Okay, great. So that's just some aside about these BPS counts. Okay, now, so the last piece of the story that I told you in general was that there's supposed to be some complex integrable system associated to an n equals 2 theory. So given gamma and z, I said you can build a complex integrable system. And in our particular case of these theories of class S, where all the data that we start with is just a Riemann surface with some punctures, then I can say pretty concretely what this integrable system is. What it is it's the moduli space of SL2 Higgs bundles over the surface. And I wrote here what's the definition of an SL2 Higgs bundle. It's a pair of E and phi, where E is just a holomorphic rank 2 vector bundle over the surface with trivial determinant. And phi is like a holomorphic one-form valued endomorphism. So that should say phi is a section of NE tensor KC. Phi is a global one-form valued endomorphism of the vector bundle. And then, so given one of those Higgs bundles, okay, so M, our complex integrable system, is the moduli space of those Higgs bundles. And it's supposed to have a projection to the moduli meromorphic quadratic differentials. What is that projection? Well, it's just that given the Higgs bundle E and phi, I have my matrix valued endomorphism. Sorry, my one form valued endomorphism. I can take the square of it and then take the trace of that, and that gives me a holomorphic quadratic differential. That's in the case without punctures. In the case with punctures, there's a sort of similar story where you have to allow singularities at the punctures. So you consider now Higgs bundles with singularities at the punctures an appropriate kind. Roughly speaking, it just means that the Higgs field, this matrix, this one form valued endomorphism is now allowed to have poles. Okay. Okay. So far I've been telling you essentially the background, and now I want to start getting to the what are we going to construct. So one of the key things about this space M, so I described it as a kind of abstract complex integrable system, but it has a meaning in physics, and its meaning is actually quite parallel to the meaning of the Coulomb branch B. So the meaning of B was, it was the vacuum configurations of the theory in R4. You can think of this, the total space of this complex integrable system in a similar way. It's also the vacuum configurations of the theory, but now formulated in R3 cross S1. In particular, the consequence of that that's important for us is that M should have a hyperkähler metric, in fact, a family of hyperkähler metrics, depending on a parameter. And that parameter you can think of as being the radius of this circle in the spacetime. Okay, so what does it mean concretely to say that the space is hyperkähler? So after fixing this parameter R, so then it has to get the following structure. So first of all, being hyperkähler means that it has not just one complex structure, but a whole family of them, parametrized by CP1. The two sphere of them, you can think of it as like the unit imaginary quaternions. But in fact, one of the big insights in this subject, due to Hitchin, is that, maybe due to Penrose and Hitchin, is that it's good to think of that S2 as actually being CP1. Okay, so when I described this space to you, I described it as a complex space. I said it's a complex integrable system. And so one of these complex structures is the one we already discussed, and that's the one at zeta equals 0, at the north pole of the twistor sphere, as I'm drawing it. And then these complex structures have to obey the quaternion relations, where I, J, and K are the 3 points that I've indicated on this picture. And then it has to say that a metric is hyperkähler is to say that it is Kähler, a single metric, which is Kähler with respect to all of the complex structures at once. And so in particular, whenever you have a Kähler metric, you get a symplectic form. And so we have a whole pile of symplectic forms. They're all linear combinations of 3 of them, the symplectic forms corresponding to, say, I, J, and K. So this is a space which is Kähler in many different ways, in sort of a CP1 worth of ways. Now, okay, so what is this hyperkähler structure in our kind of running example? So in that case, I said the space we're studying is the moduli space of Higgs bundles on the surface, and in that case, the statement that it has a hyperkähler metric is not a new statement from physics. It was known before from gauge theory, work of Hitchin, Simpson, and in the wild puncture case, and Bulch. But the construction of it, I just want to indicate how you construct this metric in practice. What you do is you take this kind of nice algebraic space that I described for you, the moduli space of Higgs bundles, and you have to identify it as the space of solutions of a certain nonlinear partial differential equation on the surface. So I wrote that equation here. So if someone gives you a Higgs bundle, what you look for a Hermitian metric in the bundle that obeys an equation. And the equation says that the curvature of the Chern connection is not 0. You don't ask the Chern connection to be flat, but you ask it to be equal to the commutator of the Higgs field and its adjoint up to this factor of R squared. anyway, the details of the equation aren't important enough to say that it's because SLN is nonlinear, because SLN is non-abelian, particularly SL2 is non-abelian. This is some elliptic nonlinear PDE. But then the big theorem is that there actually is a unique such metric once you impose appropriate boundary conditions and appropriate stability conditions. And so you can identify M with the space of solutions of this equation. And then in particular, you can use that to define a kind of L2 metric on M, where when you perturb a little bit along M, you get a perturbation of the solution, and you can use the metric to use H to define the norm of that solution. That gives you a metric on this moduli space, and that's the one which miraculously is hyperkähler. Now, that description is a kind of abstract existence. If all you know about the solution of Hitchin equations is kind of abstract existence theorem, then essentially all you get about the metric on the moduli space of Higgs bundles is also a kind of abstract existence theorem. You know that it's hyperkähler, but you don't know much else. And it's been hard to get concrete formulas from this point of view, although recently, actually, there's been some progress. So the Riemann-Hilbert story that I'm going to describe, coming from physics, is a kind of conjectural alternative way. If I specialize it to this example, is a conjectural alternative way of describing this metric, which will look totally different. It'll have nothing to do with solving PDEs or anything. The claim is that nevertheless it produces the same metric. That's the conjecture. Okay, so how are we gonna produce this hyperkähler space? Well, the way we're gonna do it is somehow not to think of it head on. Is not to try to write down a formula for the metric directly. That's somehow very hard. Instead, we want to get back into a situation where it's more or less a complex analytic story. And it turns out it's possible to do that. The trick is, instead of thinking about the hyperkähler space M directly, you think about its twistor space. What is its twistor space? The twistor space is this higher dimensional complex manifold, which kind of assembles all the complex structures of M into a single holomorphic family. So the picture is like this. So the twistor space is diffeomorphic to just M cross CP1. So each fiber, and has a projection down to CP1, which is a holomorphic projection. So the picture is each fiber of this thing is this is the third thing. Each fiber of this projection is diffeomorphic to M. And complex analytically, it's M with its complex structure I zeta. So if you look at all the individual fibers here, you're seeing this hyperkähler manifold M in all of its different complex structures. But the miracle is that they can all be organized into a complex manifold. So what you're saying is that the complex structure itself kind of varies holomorphically as a function of zeta. That's the cool thing about hyperkähler manifolds. So the twistor space, it has the holomorphic projection. Each fiber is like M in a different complex structure. Another important thing about it is that, so because it's diffeomorphic to M cross CP1, it has these canonical sections. I've indicated one of them in red. So each point of M corresponds to a section of this twistor space. And those sections are holomorphic. And sort of following along those sections gives you the diffeomorphism between the different fibers, identifies them all with M. And then the last thing is that, so M had all these, had complex structure, but also all these Kähler forms. And to get the metric, you need the Kähler forms. So the way that those appear in the twistor space is actually as a fiber-wise holomorphic symplectic form. So it again gets recoded into holomorphic data. And so, okay, so the idea is that instead of describing a hyperkähler manifold directly, you try to describe instead this twistor space, which is an object of complex geometry with a holomorphic symplectic structure. Plus, of course, you have to give these twistor lines. You have to give the identification of it with M. Okay. Okay, and so in order to try to understand this hyperkähler space, what we're going to do is we're going to try to understand its twistor space. Okay, and so now here's the conjecture. The conjecture is that the twistor space is not just a complex manifold, but actually admits some very distinguished set of coordinates, piecewise holomorphic Darboux coordinate system. So the piecewise holomorphic is kind of a funny thing. So the picture is going to be, one way to think of it is that you have these walls, you have a kind of wall and chamber decomposition inside of the twistor space. And in each chamber, you have a distinguished holomorphic coordinate system. And then this holomorphic coordinate system jumps by some symplectic transformation when you cross from one chamber to another. And so knowing the Darboux coordinates is enough to determine the holomorphic symplectic form. I'm just saying if you know P and Q, then you know dP wedge dQ. So what we're going to do is we're going to give the local P and Qs. So there'll be these functions, we call them X gamma, gamma labeling a vector in our lattice, capital gamma. And the statement is that the conjecture is that these piecewise holomorphic coordinates can be determined, thought of as functions on the C infinity manifold M cross CP1. You can determine them by solving a certain Riemann-Hilbert problem. Okay, so let me now formulate that problem. So let me remind you that the data that we have. So this is a thing which we do independently at each point of the manifold. So let's pick a point, and let me pick it to be lying on a generic fiber. So not one of the singular torus fibers, but just pick some regular torus and pick a point of that fiber. Then what's the data that we have? So we have these central charge functions Z gamma. We could evaluate them at the particular point that we're at, actually project the point down to B and then evaluate those functions. Okay, so we have a bunch of complex numbers. Then our point is a point of the fiber of this, a point of one of these torus fibers. And so we have the fiber coordinates, which are kind of like angle coordinates. You can think of that as a function from gamma to the circle. And then we have these integers, omega of gamma. And that's the data that we're going to use to construct the coordinates. So okay, so what are we looking for? So we're gonna look for we're gonna construct all the coordinates at once. Somehow this is a coupled problem. You can't construct just one of them separately. You have to construct them all at once. So they're functions from C star to C star, where the C star on the left is the zeta coordinate. So one function for each lattice vector, and the properties that they should have. Okay, so here's a list of the properties that they should have. They're going to be multiplicative. They're going to be piecewise analytic with some specific kind of jumps. They're going to have specific asymptotic behavior as the parameter zeta goes to 0 or infinity. So on the twistor sphere, the picture is going to be that there's the North Pole and the South Pole, and those points are very different from all the other points. And we're going to construct things on the kind of central C star, and then they're going to have some singularities as zeta goes to 0 and infinity. Then there's going to be a reality condition that relates what happens at 0 and what happens in infinity. And this is going to be a kind of gauge condition which you put in to try to make the solution unique. And the picture is going to be what we're hoping for is that functions obeying this list of properties exist, and moreover that they're uniquely determined by this list of properties. That's the dream. So let me now say a little more precisely what these properties are. Okay, so the multiplicative thing is pretty easy. So we're constructing the function. So remember now we've fixed the point of our hyperkähler manifold, our 2D hyperkähler manifold. We fixed the point, and we're just looking at the dependence on the twistor coordinate, this coordinate zeta, which keeps track of the complex structures on the space. And so for each vector gamma, we're supposed to have a function of the twistor coordinate, a function x gamma of zeta. And those functions, you have one for each lattice vector, but they're multiplicative. So x gamma, x mu is x gamma plus mu. So that means another way of thinking of this is that rather than giving a whole bunch of functions, you could say that what we're giving is a map to a torus, the torus of C star valued characters. So what we're after is then some map from the twistor C star to the torus, complex torus. Okay, and this map. Now, the interesting thing about this map is that it's not supposed to be analytic. Analytic as a function of zeta, but rather it's going to be piecewise analytic as a function of zeta. And so I drew a picture of what it's supposed to look like in the zeta plane. So there are these domains separated by rays going from 0 to infinity. And there's one ray, roughly speaking, there's one ray for each BPS particle. The rays are labeled by the gammas for which omega of gamma is not equal to 0. So I showed you an example earlier, this A1, A2 example, where there were only 4 non-zero invariants. Omega was supported in 4 places. And in that case, the functions which we build would be analytic away from 4 rays. This is a picture of what those 4 rays might look like. Their angle is determined by this Z gamma. So the angle of the ray is just the argument of Z gamma. And on the right, I drew the same picture. So on the twistor sphere, you would think that you're kind of marking a bunch of meridians, and your function is going to be analytic in the domains separated by these meridians. And then when you cross a meridian, the function is going to jump. And the way that it jumps is precise. You don't just say it jumps. It jumps by this specific transformation of coordinates. It looks a little complicated here. Maybe all that's really important to say is just that this is some automorphism of the torus. So we're looking at a map. We organize these x gammas into a map to the torus. And what we're saying is that that map is, when we cross one of these rays, that map jumps by some automorphism of the torus. These automorphisms, I probably should have written Conceivich, Teubelin, and Fock-Goncharov here. These automorphisms are kind of well known in the in DT theory and cluster theory. Let me show you one example of this just to say that it's not so scary. So imagine that we had just a rank 2 lattice. And so then this map to the torus is determined just by 2 functions. I'll call them little x and little y. And suppose that we have one of these invariants, omega gamma 1 is equal to 1. Then the statement is that when we go across the ray L gamma 1, whose position is determined by this Z gamma 1, when we go across that ray, the function x will actually be holomorphic. It doesn't jump, so x plus, the limits from the 2 sides, x plus and x minus, are just equal. The y coordinate jumps, but it just jumps by multiplication by 1 plus x. So it's that kind of, explicit algebraic transformation that you're talking about. Okay, and so part of this Riemann-Hilbert problem is we're looking for a collection of functions with these very specific jumps as you move around in the zeta plane. Then, okay, so this x gamma is supposed to be piecewise analytic as a function of zeta in C star. Then you ask, what happens when zeta goes to 0? Well, we'll get to infinity in a minute. First, let's just ask what happens when zeta goes to 0. And then the statement is that it has a kind of characteristic asymptotic behavior. It goes like this function here, which has an essential singularity. So the behavior is like that of a function with an essential singularity as zeta goes to 0. It's like exponential of 1 over zeta. And the precise asymptotic, so the leading asymptotic is controlled by this Z gamma divided by zeta, multiplied by this scaling factor R, but basically it's controlled by Z gamma, the central charge. And then there's a subleading part that's controlled by the theta gamma, where you are on the torus. And then unfortunately, there's also some error, which I call delta gamma. Let me not worry too much about that for now. The simplest case to think of is, in the case where we understand it best, is actually the case where we choose the angles to be 0. So then we're looking at some distinguished section of the integrable system where the angles are 0. And in that case, this formula just says that the x gamma, as zeta goes to 0, it behaves exponentially, like exponential of R Z gamma over zeta. And that's supposed to be true, crucially, that's supposed to be true when you go along any ray. So despite the fact that the function has these kind of, these non-analytic jumps as you move from one ray to another, the statement is that those jumps are invisible in the zeta goes to zero asymptotics. The zeta goes to zero asymptotics is given by this simple analytic formula. And in fact, that's somehow the tension with this space. There's some tension between having a nice uniform asymptotic behavior and being actually analytic. You kind of have to choose one or the other. So here we're choosing to have the good asymptotics in every direction, and the price we pay is that the thing is not analytic. Okay. Then there's another condition, which is that when you make the antipodal transformation, zeta goes to -1 over zeta bar, that these coordinates behave in kind of a simple way. Roughly x goes to x bar. And that's kind of just inherited from the fact that the twistor space itself has that property that when you make the antipodal map, it just corresponds to reversing the complex structure. And also take the homomorphic symplectic form of its complex conjugate. So everything should have a simple transformation to that, and it does. And so in particular, I don't have to tell you the asymptotics at infinity. So the asymptotics at infinity are kind of the same as the asymptotics at zero. This, let me just say, just as an advertisement for the next talk, I guess I'll just say that this is where we kind of, this is the place where this story really differs from the story that that Tom Bridgeland and others are investigating now. There's another version of this Riemann-Hilbert problem where you don't put this reality condition, instead you put something else. Okay, but for the application to real hyperkähler geometry that we're talking about, we want that reality condition. Okay, and then there's some slightly technical condition where we restrict the asymptotic behavior. We want to put some condition on the order 1 part of the asymptotic behavior. Roughly, we don't want to fix it completely, but we want to restrict it just enough to make the solution unique. So for example, we could require that this delta gamma is real, and that would be expected to make the solution unique. If you don't impose any condition, then the solution is not unique. The failure to be unique is just diffeomorphisms of the torus fiber. So you're not constructing a hyperkähler manifold, you're sort of constructing a hyperkähler manifold up to diffeomorphism. Maybe that's okay, but concretely, in order to solve this thing, I don't know how to solve it without putting some actual condition. Okay, so now I've formulated this problem, this Riemann-Hilbert problem with these 5 conditions. And now, okay, so the conjecture is that by solving this problem, you'll get a construction of a hyperkähler manifold, for example, a moduli space of Higgs bundles. Okay, so now we should ask, that's a conjecture. What's actually known about the solutions? So I think that little is known in general about the kind of abstract problem. I mean, it's clear that they can't exist without some conditions on these omega gammas. You don't want them to grow too fast. In examples, at least, you can try. There is a recipe for constructing solutions where you write down an integral equation. I wrote this integral equation here, which just involves the data of, so you see the x gammas appear on both the right side and the left side of this equation. So it's really an integral equation, not an integral formula. They're being integrated over, that integral over L gamma should say integral over L mu. So each x mu is getting integrated over the corresponding ray L mu with coefficient given by this number omega mu. So you see all the basic ingredients, the z gamma, the theta gamma, and the omega mu, all get just put into this integral equation. And this equation is engineered exactly so that its solutions, if it had solutions, they would have the properties that they're supposed to have. In particular, you might ask, where does the piecewise analyticity come from? And it comes from the fact that when zeta crosses one of these rays L mu, there's a zeta minus zeta prime in the in the integrand, and that zeta minus zeta prime becomes singular. So you pick up a residue. Okay, so this integral equation is engineered so that if you could find a solution of it, it would hopefully be a solution of the Riemann-Hilbert problem. And this you can try to do. So there are some arguments that suggest that you might be able to actually do this just by the most naive procedure of just iterating the equation. So you plug in some initial gas, then you put that on the right-hand side, calculate the left-hand side, plug that in on the right-hand side, and repeat. So think of it as a fixed point of some integral operator. And so there are some arguments that suggest that this is going to work, at least for sufficiently large value of this parameter r, and when you're far enough away from the singular fibers, when you're on kind of the large Born part of the of this complex interval system. There's a curious fact, which I don't know why it's true, and I'd really like to know why it's true, which is that you can experimentally try doing this, like literally try solving this integral equation in some examples. And the experimental fact is that if you look at, what I said was the nicest part, the part where theta equals 0, then this same method works even for small value of r. I don't know why it is. The most naive arguments don't show that it would work. So I'd very much like to know actually why it works. Just a concrete question about this integral equation. Now, okay, so one thing is that you can kind of experimentally try to produce solutions of this equation. Now, then you could ask, are those functions actually doing what they're supposed to be doing? So there's some evidence that the procedure actually works. So let me talk again about this most basic example that I showed you, the example, what I call the A1, A2 example, where we're just studying this concrete family of cubic curves with either 4 or 6 non-zero invariants. So there we can solve this integral equation by the kind of iteration procedure that I told you, that I just sketcch, specifically on the locus where theta equals 0. And then once you've computed these holomorphic coordinates on the twistor space, I told you that's supposed to determine the hyperkähler metric, and indeed you can really you can compute numerically what the hyperkähler metric is using these functions x gamma. And so here's a picture of the output in a particularly simple case. So suppose I take that parameter. We had a parameter that controlled the linear part of the polynomial, but suppose I set that part to 0. So I just write the polynomial, the quadratic differential z cubed plus a constant. And so that constant, that c, is a complex number. So in this case, our integrable system is complex 2-dimensional, but we're just studying a section of the integrable system. So we're just studying the complex plane. We're studying a metric on the complex plane. So it's the restriction of this hyperkähler metric to that plane. Then it's just a Kähler metric. And moreover, there's a sort of rotation invariance in the story. Just by taking z goes to e to the I theta times z. That can be undone at the cost of rescaling the parameter z, the parameter c, and because of that, everything only depends on the absolute value of c. And so ultimately, the metric, I'm writing it g c sub bar. That's c c bar. That's the metric coefficient. It depends only on the absolute value of c. And so you can just plot that function. And so in the left frame here, I'm showing, okay, the plus and the x are two different ways of computing that metric coefficient. So the x is using these integral equations. The plus is the kind of direct way. So I told you that this metric can be computed concretely by solving an elliptic PDE and then taking an L2 norm. And so that, on a complicated Riemann surface, that seems hard to do, but in this example, in the plane, you can actually do it. You can just numerically solve that PDE and compute the metric that way. And so I plotted pluses for the metric coefficient computed that way. And what you see in the picture, hopefully, is that you don't see pluses or crosses, you just see these little stars. And so that indicates the agreement between the two computations. The dashed line is a kind of asymptotic formula. Okay, maybe I don't say more about that. Well, no, I will say more about that. So the dashed line, sorry, the dashed line is what you would get if all the BPS invariants were 0. So there are these omega gamma, which I said are kind of the key players in the story. So you can say what happens if the omega gammas are 0, then you also get a formula for the metric, it's this dashed line. And so, yeah, okay. So far out on the moduli space, that's actually a very good approximation. But close into the center, where these BPS particles get lighter and lighter, the center charges get smaller and smaller, their contributions become more and more important. Okay, and on the right is the residuals. So the residual is pretty small. Okay. So, okay, I guess the last thing I want to say is, so I just told you some kind of abstract thing that there's a Riemann-Hilbert problem that we would like to solve, which if we could solve it would produce coordinates on this hyperkähler space, particularly nice coordinates on this hyperkähler space. And then we had this class of concrete examples where the moduli space that we're after is the moduli space of Higgs bundles. So you could ask, you know, here you're giving some concrete functions on moduli space of Higgs bundles. So what are those functions? Well, in that case, we can understand them concretely, at least somewhat concretely. And the reason is that this hyperkähler manifold is not something totally abstract. I told you its description at zeta equals 0. Then it was the moduli space of Higgs. Oh, I see. I'm a little over. Okay, this is the last slide. It should be only 1 or 2 minutes, if that's all right. Okay. So for any zeta in C star, this moduli space is holomorphically identified with the moduli space of flat SL2C connections over the curve. And so what that means is that each one of the twister lines, those lines that I drew cutting through the twister space, each one of those twister lines corresponds to some family, some one parameter family of SL2C connections. For each value of zeta, you get an SL2C connection. On the other hand, at zeta equals 0 and infinity, it's different. So this family of SL2C connections doesn't have to be regular as zeta goes to 0 and infinity. And in fact, it blows up as zeta goes to 0 and infinity. So you're studying this singular family of connections. So a point of this hyperkähler manifold is equivalent to this family of connections that's blowing up as zeta goes to 0 or zeta goes to infinity. And so all I want to say is that in this case, the functions x gamma of zeta, which are supposed to solve the Riemann-Hilbert problem, you can describe them explicitly in terms of the solutions of in terms of the flat sections of this SL2C connection. And then to check that they have the expected properties, well, the only property that's hard to check once you've correctly defined these functions, the property that's hard to check is that they have the right asymptotics. That involves so-called WKB analysis, studying this kind of singular family of connections. And I think that, well, I'm not sure. I hope to learn from Nikita's talk, actually, whether today it's proved that this family that this particular family of connections has the behavior it's supposed to have. If not, I'm hopeful that it will be proved soon. Great. So, and then I'm going to start from there next time. So then I want to get to the stuff about topological strings, but this is a good place to stop now. So thank you.
Thank you very much. So I think we have already a question in the chat. Arpan.
Oh yeah, this is a great question. Okay, so the question is this equation, right? You look at this equation. You look at this equation, and if you're, the right kind of physicist, you say, oh, wait a minute, that's exactly that looks just like the equation of this thing called the thermodynamic beta ansatz for a massive two-dimensional integrable system. And so the question is there any reason why the same equation is appearing here? This didn't obviously have anything to do with, this two-dimensional massive integrable model. It looks like it has to do with a four-dimensional field theory. I don't know the answer. The last I talked to, other people who thought about this, they didn't know the answer either. There must be a cool answer to this, but we don't know it.
More questions?
I have a question. I have two questions actually. About the R is the radius in of the force direction, right?
R was the radius of the circle
Of
direction.
the
Yeah,
circle,
R3
yes.
press S1.
So what is theta in the 4D physics, in the 4D to 3D physics?
Oh, theta is like the holonomy. So it's nothing in the 4-dimensional physics, but when you go down from 4 dimensions to 3 dimensions, you had a bunch of U1 gauge fields in the infrared, and it's the holonomies of those U1 gauge fields around the circle.
Okay. And so you were saying that even though it's an extension in at large R, right, that you could say something about the R to 0 limit. So
Did I say that?
well, that it was valid for small r at least.
I said that, right. Surprisingly, I mean, this integral equation in principle is not supposed to be an expansion. I mean, the equation is supposed to be exact. It's just that the method of solving it by iteration, it's not clear, the kind of estimates that show you that iteration would actually converge, those estimates only work at large value of R. And it is for the kind of the reason that you would think. I mean, from physics point of view, you would say, well, the contributions from BPS particles going around that circle are going to be more suppressed the larger R is.
Right.
But the equation is not supposed to be an expansion. It's supposed to be an exact equation. So if you can solve it, you're in good shape. And for whatever reason, it seems that you can solve it even in domains where you might not have thought you could solve it.
So in your A1, A2 example, do you know what it would like? What would the metric look like at small r? I mean,
yeah. So oh yeah, good point. So in this example, in fact, I didn't say what R was. So implicitly, R was 1 in this picture. Now let's see. In this case, well, in this example, the theory is conformal, so R can just be rescaled away. Now you might ask, what happens when I introduce that lambda parameter? Then what's the small r? Right. I think I know the point of your question. If you set up the limit correctly, you can get something interesting where in the strict 3-dimensional limit, it has to kind of decompactify the torus fibers.
Right. I think from 5D physics, well, we have this argument that in the 3D limit, it should just be in that case, for instance, just flat hyperscalar like H. Right. So 1-dimensional space. And
in which theory?
So this one is like this is A1, A2, right? Is so it's like this the first Argas.
Oh, in that one, okay. But with this deformation lambda turn on or not?
I think no. I mean, I want to really say just the CFT on circle.
Probably just literally the conformal theory.
Just the conformal, but then you flow to what would be some kind of fixed point in 3D, but it's supposed to be just then
it should be flat. I think I agree. If you sort of expand around a fixed point in the right way, then I think it should be flat. But that you don't see so directly from this. At least I don't know how to see that directly from this construction.
I see. Cool.
Peter?
In the slide when you were describing the expected asymptotics of these x gamma, so there is this theta and delta. Is that a nasty question to ask to expand on that a bit?
No, it's a very reasonable question. But so I think the deal is like this. So first of all, if you don't put any condition on that delta, then there's nothing wrong with the problem except that it has no right to have a unique solution, because you can always act with kind of diffeomorphism on the thetas. Now, then the question is, what's a good condition to put on this delta? And for a while, I thought that the good condition was to require it to be real. that sort of looks obviously orthogonal to the theta direction, right? The way I've written it here. That's kind of transverse to the diffeomorphisms of theta. And indeed, if I remember right, this method of solving by the integral equation, I think automatically picks that gauge, meaning that if you get a solution, it's going to have that property. In particular, I think that that property does occur for the one basic solvable example, the Ogrieva example. Now, the funny thing is that if you do the WKB thing, if you do the WKB analysis of this family of Higgs bundles, and you ask what's going to be the first subleading asymptotic, and you think that theta gamma is like the usual coordinates on the Jacobian, I mean kind of the standard coordinate system on the moduli of Higgs bundles, then I think you find that this delta is not real. Now it obeys some other condition. It's kind of type 1, 0. It has to do with the integral of a 1, 0 form over the spectral curve. So there's a different natural condition that you could impose if you wanted to produce exactly that solution. The solution which would come, most naturally from applying WKB to this family of connections. So that's the kind of thing that has to be ironed out before we can completely understand the story at non-zero values of theta. At theta equals 0, we don't have this problem.
Do you have a kind of a geometric guess for what it could be? So, for instance, Z gamma has a very, very nice geometric picture, right? You're just doing these periods. Do you?
Yeah. Delta gamma. It also has some nice. It's the holonomy of some specific connection that you get by I forget exactly what it is, but it's some simple construction that you do using the solution of Hitchin equations.
I see.
Yeah, we could talk about it. Yeah.
Cool. Thank you.
Maybe one more quick question. If not, let's thank Andy again. And maybe we can resume at 5 minutes class. I don't know, actually. Yeah. No, but maybe in a couple of minutes. Yeah, and I should post your slide as well, sir.
Yeah, I hope they are not too heavy. Well, maybe I can already try to share the screen sometimes.
Yep.
The iPad is not cooperating.
Oh, I think I have them already. Well, I should stop recording.